Hello, thank you everyone to attend my presentation. My name is Flavio Ceolin. I work for Intel and I have been contributing with Zephyr for the last 6 years. I'm the current maintainer of the power management subsystem, and I'm also involved in other areas of the project. The presentation today, it's about power management, and my goal here is to provide a good overview of the features and the architectural framework that underpins Zephyr's power management capabilities. Additionally, I will also provide some guidelines to use and implement power management. So why we care about power management, right? These are just a few reasons. First, to extend battery life, provide longer battery life for devices is very crucial for battery-powered IoT and wearable devices. Another good reason to care about power management is cost savings. Lower energy consumption translates directly to cost savings, and it makes products more competitive in the market. Another reason is environmental impact. Since reducing power consumption contributes to lower carbon emissions. Regular compliance, it's another reason. Many regions have regulations to energy consumption for electronic devices, so we need to be aware of this. And even in user experience, less frequent charging, it's related with more user satisfaction. Definitely there are other reasons here, just a few. So these are the topics that I will cover today. I will start with the design and goals, and then I will cover power management implementation on Zephyr and finish with how to enable and use it. Hopefully, we will have some room for questions as well in the end of the presentation. Okay, so designing objectives. First and more obvious, we want to reduce power consumption, right? We want to provide a way to consume as little energy as possible while we are still meeting functional requirements for a given use case and configuration. Secondly, this must be flexible. Different use cases and configurations have different power and functional requirements. Then it's mandatory to maintain responsiveness for the system. The system must be able to properly respond to events. Like be flexible, it must scale. It must scale from simple constrained devices to much more complex systems. And we aim to do this as much abstract as possible, providing a consistent interface for applications, as many other areas on the project. So what the subsystem does is provide mechanisms for a collaborative model where different parts of Zephyr, like device drivers, subsystems, and applications can work together to meet these objectives. So here are some key concepts that will help to navigate through Zephyr's power management. The first concept is kernel idling. Kernel idling, as we are going to see later, it's the code that is executed every time the system has nothing to do because all the threads are blocked waiting some condition. It's basically here where the system power management happens. Then we will go to the power management subsystem, see that the power management subsystem is divided in two major areas, system power management and device power management. System power management is done in the idle thread, as I mentioned, and it's responsible to save energy changing the associated power state. So power state can also be called idle state or sleep state, depending on the nomenclature, depending on the document that you see. On Zephyr, we mostly use power states for this. An important component of the system power management is the policy manager that we will see. The policy is responsible to make the decision about which power state should be used when the system gets idle, and based on the events and the possible conditions that were imposed to this policy. Like power constraints and latest constraints can be set to the policy that will change the decision that the policy can make. We are going to see later how the full policy works and how an application can change the behavior of this policy. The other major area that we'll see is device power management, that it's responsible to save energy, suspend devices. Device power management can also be, static or dynamic. The static, it's when the devices are suspended together with the system. So when the system goes idle, we suspend the devices, and when it wakes up, we just resume them. And dynamic, on the other hand, it's more ad hoc. Devices can automatically, suspend and resume themselves. An example of device runtime is a UART. UART can get a reference from a GPIO driver when it's needed and release this when it's not needed anymore. If no one else is using this GPIO, the GPIO will be suspended. This dynamic device power management on Zephyr we call device runtime power management. So let's start with the system power management. So to understand the system power management, we have first to talk about a little bit about the scheduler and the idle thread. The scheduler is the main power management governance, since it knows when the next event will happen, and consequently can knows when to start doing power management. The Zephyr scheduler, it's a priority-based scheduler with optional round-robin time slicing. And this means that the scheduler will run first high-priority threads. So as you can see in this diagram, the scheduler will execute thread 1, then when thread 1 reaches a reschedule point that can be, for instance, caused by waiting on a semaphore, or yielding, or sleeping, this thread is marked as suspended or waiting. Then it will do the same for thread 2, thread 3, so on and so forth. Finally, when all these threads are suspended or waiting some condition, the scheduler will go and schedule a special thread that it's the idle thread. There is one idle thread per CPU, and it's created with the lowest priority. So this ensures that the idle thread is executed only when there is nothing else to do. One important thing to mention here is that Zephyr kernel is stickless capable, which means that the kernel is fully event driven, so there is no periodic clock interrupting the system. So here we have a high-level diagram of the idle thread. It's basically a continuous loop that every iteration locks IRQs to avoid being preempted during the power management sequence. Then if the target does not support power management, the idle thread just restore interruptions and put the CPU idle waiting for some event to happen. Now, when the system supports power management, then the idle thread will call the PM subsystem with the number, with the amount of the time to the next event that it's scheduled. The subsystem then may or may not suspend the CPU based on possible constraints, or if the time is enough to use one of these sleep states. If the CPU is not suspended, then it's exactly as if power management was disabled. Then the idle thread will just behave like without power management, just unlocking the IRQs and waiting for an event. And that it's all for the idle thread, basically. The key or trick part here is that at the end of the loop, interruptions has to be unlocked. So it's a little bit tricky because you start with the interruptions locked, and then you do power management, and at the end of this you have to remember to restore interruptions. So from that perspective, system power management happens inside this function called PM system suspend, the highlighted box here. So this diagram on the left abstracts what the system power management basically does. In a nutshell, it checks with the policy manager which power state should be used based on the amount of the time to the next event. If the policy returns a state that it's different from active or runtime idle, the devices are suspended. I will talk about this later, but obviously this depends on device power management be enabled. And after this, the subsystem will call SOC API asking to transition to this state that the policy return. When the CPU wakes up, the subsystem will, revert what was done. So we'll resume all the devices and finally, call this another SOC API that it's basically restore to give the system full operational again. And it's expected, when you return from this function that the IRQs are unlocked. So power states. Power states for Zephyr, it's a way to describe, the multiple power mode savings supported by the hardware, and they were, inspired by the ACPI system states. These states, they have to be, declared in the device tree, so they can be accessible by other components in the system, like the policy manager. That we will use this information to, to select which state the CPU should be suspended. So we have 7 states counting the active state on Zephyr. The states go from active, where the system is fully, powered, to soft off, where that it's the deepest sleep state available, and that it's the one that consumes the minimal amount of power. Of course, as GPU is the state in this list, more is the energy that it's saved, but also it's bigger the time to transitioning and to leave from these states and to wake up the system. So platforms should, map their states to these ones. And in most cases, obviously, they don't have all these states, and that it's fine. They need to declare only the states that are supported by the hardware. There may be certain cases where, a target has 2 sleep states that would map to a particular Zephyr state, and for these circumstances, they can use a substate that would be, specific for this target. One important note here is Zephyr does not really impose which states the target has to implement, and we don't even, impose what has to be done in this state. We just provide, a general guideline and some expectations, but not really impose any behavior for these states. The policy will select which state that it's passed directly to, basically, the state that it's returned from the policy would be passed directly to the SOC. And the SOC, it's up to the SOC to do whatever it wants with this state. So on the left, I have a full representation of the power state in the device tree, right? Besides the state itself, we have other 2 properties that are a minimal residence, and that tell us the minimal time that the system should stay idle to be worthwhile energy-wise speaking. And as an exit latency, that it's the amount of time required to the system exit this state and become active. These informations are used by the subsystem to program the timer in a way that the system does not miss any schedule event. So in the other side, you can see the definition of the power state in C, and in this declaration, you will find description of which states it's equivalent, a description of the state and equivalence to ACPI when you are trying to do this map. Okay, so moving to the policy manager. The policy manager, as I have said, it's one function that it's called from the idle thread with the number of ticks to the next event, and it's responsible to return a sleep state or a power state. The default policy, it's based on residence time, and the logic is pretty simple. So it selects the deepest state available, that the minimum, so it selects the deepest state available, that the minimum residence is lesser than the time to the next event. the policy also accounts for, for the state and latency constraints that can be imposed by applications or subsystems. Applications can also, define their own policy. There is one symbol that they have to select, and then it's up to the application to create your own policy, define this function. There is one function here that it's this PM state force, that it's a way to bypass the decision of the policy. So if the application decides, to force the system to go to a specific state, can use this API. And in this case, the system power management will not even ask the policy what it's going to be the next state. The other, major area in power management on Zephyr is device power management. So first, device power management, it's enabled selecting the symbol PM device, and to support power management, drivers need to implement an interface that it's a callback, action callback that receives, an action that should be taken. This boils down to handle requests to suspend and resume the device. And in some cases, if the device belongs to a power domain, then you also need to to handle turn on and turn off. I have mentioned it, but on Zephyr we have these two methods to do device power management. It's the static and dynamic. So static, it's also called system management power management. It's the one that when the system goes idle, we suspend and resume, and when the system wakes up, we resume these devices. Dynamic or runtime power management, that it's the nomenclature that it's more used, is the capability of suspend or resume devices automatically according with their usage, and that does not depend on the system power management. Does not depend on the system be idle to happen. One note, regarding system management, system managed power management, device power management, is that devices are suspended and resumed with their according with their dependencies. So it's we use the same dependencies that are used for device initialization. So we suspend device according with their initialization, then we revert this when waken them. So coming back to the system power management diagram, after the policy returns the state that should be used, if it's anything, then active runtime, devices are sequentially suspended. The subsystem ignores some devices that depend on some conditions, like if the device is busy, or if the device is using runtime power management, or the device is used as a wake-up source, then the system excludes this device from this list. Then after the SOC wakes, the devices are resumed in a reverse order that they were suspended. In a multi-core system, only the last CPU, only when the last CPU is going to sleep is that the devices are suspended, and as soon as the first CPU wakes, devices are resumed. Okay, so here's the part of Zephyr's code that checks the conditions for a device to suspend. So as you can see, if the device is not ready, or it's busy, or it's used as a wake up, or it's using runtime, then devices are not suspended. There is one option that you can even tune this, that it's PM need all devices idle, that if this option is enabled, if there is at least one device that it's idle, then any device is suspended. So now let's see device runtime power management. That it's the feature that allows device to directly power management even when the CPU is active. It's enabled when you select the symbol device runtime. There is no additional API that needs to be implemented. Suspend and resume, it can be done as synchronous and asynchronous. And there are many advantages of doing this, right? The system does not need to be idle to the device save energy, so you can save more energy when you do this. This also will speed up the system to the power management system, because the system does not need to suspend devices that are already using these and are already suspended, and the same applies to resume them. This method, it's a collaborative effort, so it really depends on device drivers doing the subsystems and application. So yeah, it's very important to emphasize this collaborative nature of this method, since none of these layers may have full knowledge of how to make the best decision about suspending and resuming a device. For example, a device may naively always suspend itself when it finishes an operation. This may be okay in some circumstances, but there may be some cases, where multiple operations are done, realized in a sequence, and this approach may end up, just consuming more energy than safe. The same logic applies, for other layers, like, the subsystem may attempt to suspend the device without knowing if the application will need to use this. So the subsystem uses a reference count to check, when it needs to suspend or resume a device. And this way, each component can operate without worried about, each other, so that it's. As I have mentioned, there are synchronous and asynchronous ways to do the device runtime power management. Let's start with the simplest case, that it's when, everything happens synchronously. In this example, we assume that the device is initially suspended. So as you can see, the idea is that when the application requests some operation from the device then calls PM runtime get, that will increase the reference count for this device, and calls the action callback to resume the device. Then the device do the operation that it's called, and when it finishes, the device will call the runtime put that will decrease the reference count, and finally, call the action to suspend the device. The asynchronous case, it's pretty similar. The main difference is that, when the device finishes the operation, instead of synchronously suspend the device, it calls PM device runtime put async, and the PM subsystem will, instead of call the action callback, at that moment we will schedule the operation to the system work queue to be done later. We play some tricks here to avoid unnecessary work. So if there is a request canceling an operation that it's in the queue, we just do some adjustments in the reference, and we avoid changing the state of the device. Some additional notes here: device can enable and disable runtime power management at runtime, and there is only asynchronous API to suspend devices. This is a simplified version of how it works. In several cases, the application would be calling a subsystem, and the subsystem will be talking with the device through multiple calls. And in this case, the subsystem may be the one holding the reference also to avoid these unnecessary transitions. Okay, so finally, power domains. Power domain is an abstraction to group a set of the devices that are powered by a common source. On Zephyr, support for power domain is enabled with the PM device power domain option, and they are implemented just as regular devices. What basically makes a device a power domain is its relationship with other devices. This dependence can be defined in device tree or can be done dynamically as well. Power domains are responsible to notify all the devices using it when it changes its state. So when the domain is suspended, it goes through all children devices and ask them to turn off, call the action callback with the turn off action. And when the domain is resumed, it goes through all the children and with the action turn on. If you are using device runtime power management, the subsystem will automatically suspend and resume the domain as well if needed. So the domain, if the children the application or someone needs to use a device, the device is using the runtime power management, this will automatically wake up or resume and suspend the domain if there is no one else using the domain. So the next few slides, the idea is to wrap up what is necessary to enable and implement power management in SOCs and also in drivers. So first things first, right? These are the 3 key config options that enable and disable power management features on Zephyr, basically. The first option, config PM, enables the system power management, the power management for SOC. And when this is enabled, the idle thread will call, the SOC APIs that was mentioned before. The next option is to enable device power management, because you make the device, make the system suspend and resume the device when the CPU is idle. Finally, there is this option to enable device runtime power management. The reason that we split, device runtime power management from the regular system managed power management is to save some resources. So if you're not using device runtime power management, there are a lot of data that doesn't need to be used. So we save some resources when doing that. And it's important to mention these options can all be combined. So you can use even the 2 methods to do device runtime, device power management. So when implementing power management for SOC, you have to implement these 2 functions, PM state set and the exit post operations. And if you're using the default policy manager, you have to declare the states in the device tree. So let me just make a point here. Declare power states in the device tree. It's not mandatory to execute the software. If you implement a custom policy, and you ensure that the states returned by your policy are known by the SOC, then you basically can return whatever you want. But it's really recommended to have the supported states declared in the device tree, because this information would be widely available for all the rest of the system. Another thing to remember is that interruptions need to be restored after the exit operation, post operations. This is an example of how to define power state. First, you declare which power states are supported by the target with the appropriated information, and finally you have to set per CPU which power state should be used. In multi-core systems, you can have different set of states per CPU. Following up, if you want to implement your own policy manager, there are 2 things that have to be done. First, disable the default policy, and second, implement this function, the PM policy next state. The policy is where the power state constraints and latents are accounted. So you have to account these constraints that are imposed by other parts of the system and application. So if you're writing policy and want to use a state constraint and latest constraints, you have to check this in your own policy. On my left, you see the full policy implementation, and if you can note, it iterates in a reverse order, assuming that that is another thing that is important to mention. All the power states should be declared in the correct order. So from the shallow state, the deepest state, sleep state. And then checks, if there is any lock for a specific state. If there is no lock, checks the latence, the exit latence for the state. If it's lower than the max latence, then finally, we just check the number of ticks for the next event, and we return this state. Okay, so to implement power management on a device, the very first thing to do is to implement the action callback. This callback can be called to suspend or resume the device when the system is idle, or doing device runtime power management. If the device is part of a power domain, it will also be called with when the domain is suspended or resumed. Then the next step is to define the power management infrastructure for the device using PM device define, or the device tree version, the PM device DT define for when you are using device tree to declare the device. The last step is to pass, the previously created power management infrastructure to the device when defining the device. As you can see, there are macros to do this. If the device belongs to a power domain, it can be described in the device tree using a property for a power domain, or it can be later, added to the domain using a runtime API, the PM device power domain add. For device runtime power management, there is no new API that needs to be implemented. What must be done is to make the device as much power aware, as much power as possible aware, suspend and resume devices itself when needed. Strategies about how to use this infrastructure really depends on the driver and the subsystem, or even in the application. The last piece, that I will cover implementation is power domains. They are, as I was mentioned, just devices. There is no specific API for a power domain. That said, they are a special kind of devices. When you are, implementing power management, the very first thing is that they have to declare as compatible with power domain in the device tree, or when you are, manually defining the device. The other thing that power domains need to do is to notify all the devices that are under, them. There is a functional helper to do this, so you iterate over the, children devices, and you call the action callback for these children. And there are much more about power management, other areas like if you're looking for device power management, you can set the device busy and change how it behaves for system power management or runtime power management. You can tune what is the initial state of a device. Device power management also, you have to worry about you can look for wake-up sources, define a device as wake-up source. You have APIs to turn in the policy. You can add or remove latency requirements, and there are events that you can set. So there are many other areas, but that it's basically the general idea of the capabilities of the subsystem. And I think we are open for questions. Yeah.
Just sweet. So with device power management, there doesn't seem to be a huge amount of drivers actually implementing that, at least in the upstream tree. Do you have any ideas of how that situation can be improved, or people can be incentivized, I guess, to implement that when submitting drivers?
Yeah, so the initial method for when power management was implemented on Zephyr, we had only the system management method, and that was and that it's the easiest one, that it's basically implement a callback. So most of the devices support this, but they don't support the runtime device power management that requires more effort. There are some devices that are doing this already, so I believe in that as soon as we have more use cases, more the other devices will start following this.
First of all, great presentation, Flavio. Quick question for you. So, power management, the APIs are wonderful. The thing that I think some newer parts, and maybe even some of our own parts, clock scaling and trying to save power through clock scaling. Is that something that you've considered in the system power management APIs and such?
Yeah, you are talking about changing the clock frequency, and yeah, there are some plans to support this. Obviously, there is the complexity because then you have basically to go and notify, everyone that the clock has changed, so the device has to accommodate this. But there are plans to do that.
Are you considering adding that to the existing like power management APIs, or is this going to be, or is there some thought that this would be a separate clock tree configuration kind of thing?
So yeah, I believe I don't want to overload the API, the current power management API. At least the callback to not become some I/O control API, like you have only one API with that does a lot of things. So probably this would be additional.
Great.
So this is a question actually for both probably Tom and Flavio. So Tom, I think you put in some device power management into some sensors. And so I'm curious how that plays with the runtime power management.
Yeah, that is a good question, and we've been talking about this. Sensors are definitely the most complex use case that we have right now, especially because they vary a lot and they have a lot of data, and there is calibration that they can lose if you suspended the sensor. So we are still grasping in this area. Duncan, as maintainer of the area.
Yeah, I'm a co-maintainer of theirs, but yeah, there's definitely we've definitely talked quite a bit about this. We had a great, in the sensor working group that we have going in the project. We had one of those meetings was dedicated to exactly this topic. The current API really is stateful, so you can set random attributes of a sensor. I'm going to set my sample rate. I'm going to set my range of readings. A lot of these sensors do take some time to start as well, so you don't necessarily want to be, constantly turning them off and on when it takes, 100 milliseconds to turn the thing back on and get back to where you were. So there's a lot to consider there, and but the kind of the consensus or close to consensus that I think we came to was that, in order to enable power management with sensors, they do need to sort of probably maintain the state that they had before turning them off, and then restore that state when turning them back on. Of course, the downside of that is now, all those attributes that were stored off on the sensor now need to be kept in your application's memory in Zephyr, which has a cost. But yeah, other than that, I mean, there's a newer API that might also help us here, because the current sensor API, we have this sort of ad hoc read, right? At any time after setting a bunch of attributes, you can just go, hey, go read my sensor. That's not really amenable to power management, right? So if I'm constantly, I set all my attributes, and then, I don't know, in a timer I go read my sensor once a millisecond and then turn it off, turn it back on, turn it off, turn it back on. That's not really a great story in terms of managing time and resources and things. So.
I definitely don't see the sensors doing runtime power management in itself. Definitely they will have to collaborate with the subsystem, especially because there are several sensors that do these sequential calls for the sensor, and that doesn't make any sense, right? For the sensor to suspend and resume between these calls, knowing that they are sequential.
Jump in as long as nobody else needs to. Anyway, hi Flavio, how you doing? So this is sort of a little bit of a digression, but obviously in the context of the Meteor Lake DSP, there was something of a digression from the Zephyr Power Management Framework, where instead of suspending nicely from the idle thread, they had a pre-existing architecture which would do it under affirmative control, basically by a cross CPU IPC out of the host kernel and just saying suspend now, and of course that's exactly what it did. It entered a routine that did a ad hoc kind of DIY context switch, and I'm on the record as not being real thrilled with that. Is it worth discussing anything like might be useful to the existing framework to try to maybe prevent that in the future, or guide systems to a cleaner API?
As far as I know, they are not doing this anymore. They are doing it inside the idle thread when they are suspending.
Right.
So
Yeah,
they have
exactly.
a way to force the next state and basically bypass. But and they play a lot of tricks, right? So that is one of the parts that I was talking about doing. So they basically disable some states for different cores and they let one core, be active at the time. So the framework is there and they are using, and it's. I mean, as far as I know, it's working.
Right. Yeah. You can't make people do
so.
stuff. It was just a little bit of, I think, a learning curve for them, and I was wondering if there was anything to report or.
Yeah. So when I started using this, was there were a lot of hacks that they did in the SoC layer to check if other CPUs were weak, and that was completely a mess. So they moved this upper layer, so the application now it's responsible to ensure that the policy will just select the most appropriate state for the CPU. So they put some constraint. They are starting using constraints for specific states and CPUs.
It's time.
Yeah. So thank you, everyone.